Welcome back, ladies and gentlemen. I decided just to get this over and done with. So, energy. I've already kind of alluded to the fact that there are different kinds of energy. I mentioned chemical energy with food. We talked about the fact that the Newton's cradle, that when I lift up one of the ball bearings, it's not moving yet, but it will. There's a subtle variation here. Now, the thing to understand is that all of it's energy. It's all energy all the time, and it's all the same stuff. It's all just energy, and energy is motion, and that's it. That is all there is to it. And we can expand on that, right? So if you have no energy, you can't move. If we use our analogy, if you've got no money, you can't buy anything. I mean, you can try to steal it, but the universe does not take kindly on theft. Now, much like with the money analogy, you can have some cash in, say, your wallet, and you can have some money in the bank. And if you go to the store and the store doesn't take a debit card, if you don't have any cash on hand, you can't buy anything. Right? You can't tell the store, oh yeah, I've got money, it's just not here right now. They're not going to accept that. So we give stored energy and energy that is active or on hand two different names. And the two names are ones that you've probably heard before. The first one is kinetic energy. And the second one is potential energy. Now, kinetic energy is energy that is active. It's the money you've got in your wallet right now. It's the money that you can make use of to do something. In the case of the weight that I just erased, the dumbbell falling has kinetic energy because it's falling. Potential energy is stored energy. It's energy that you can use if you manage to unlock it, right? So in the case of the money analogy, it's energy you can get if you go back to the bank and you say, hey, I'd like to take out some of my money, and they go, of course, sir and or madam, here is your cash. Thank you for your business. And that's it. Potential is stored, kinetic is free or usable. We'll go with free. We mean free in the sense that it's not tied down, not free in the sense that it's, walk away with it for nothing. So, kinetic energy, if we go into some detail, is about motion. So we usually talk about kinetic energy in terms of velocity because, motion, that's what motion is, it's velocity. So kinetic energy has the formula like so. Energy kinetic is equal to 1/2 mv squared. There it is. So objects that move have this energy, and the faster they're going, the more energy they need to do it. You'll notice that the velocity is squared rather than to the power of 1, unlike the mass. This actually has a bit of a weird quirk when it comes to early firearms. Early guns were not very good, for one, but when they first made them, they used very big bullets, musket balls, right? They were like, big things. Same size as maybe some of those ball bearings we saw in the Newton's cradle. And the idea was, if I got a big, giant piece of metal and I hit somebody with it, it's going to hurt. And that's true. But modern guns do not work that way. Modern guns have tiny bullets. But those tiny bullets move much faster. And the amount of energy that the bullet has then is very high. Now, kinetic energy is really simple, right? If it's moving, it's got kinetic energy. So if I take this thing, while it was moving, it has kinetic energy. When it stopped moving, it has no kinetic energy. So the energy had to go somewhere, right? When I throw this up, it has kinetic energy. When it stops moving, it has no energy. Very simple, very direct, very straightforward, which is a nice change for physics. Now, potential energy is about storage, and storage is always more complicated, okay? Because free energy, kinetic energy is easy. It's there, it is, moving, boom, done. Stored energy, how are we storing it? I mentioned a few. I said chemical energy. That's just a type of potential, right? It's like a subcategory or it's just another flavor. So it's like we're saying, potential energy is just ice cream, and then there are multiple flavors of ice cream, but they're all still ice cream. So potential energy could be stored as chemical energy, speaking of ice cream. Chemical energy, of course, has it in the bonds of the different atoms, and as you break the bonds, you release that energy. Oh, okay, so that's the requirement to release the energy and turn it into kinetic. Well, there's other things as well. You are using some energy right now. Acoustic energy, aka sound. Sound is the movement of air particles by, in this case, my vocal cords. There are bits of my throat that are moving back and forth very quickly. And as they move, they make the air turn into a breeze, basically, a wave, we call it. Now, you'll learn about waves in grade 12 if you continue in physics, but you don't have to worry too much about it. The key thing to understand is that the reason you can hear me is because I ate food today, and I am now using that food to move my vocal cords to talk. Mouth is involved too. And as the air comes out, it produces a wave, and that wave expands outward, and it would be, if you were in the classroom, it would eventually hit your ear, and as it goes inside your ear, it would activate all the different pieces inside your ear, and your ear would turn all of those signals into sound that your brain can understand. This is why, for example, it is very hard to talk underwater, because water behaves differently than air when it comes to the propagation, movement of sound, and your ears aren't designed to handle water. This is also why, for example, there's no sound in space, because there's no material, no medium for the air, for the sound to travel through. Now, of course, you're doing all of this from home, which means that another type of energy is being involved as well. Electricity. Electricity is also energy. Electricity is just energy that is stored and travels through wires in the form of electrons. Again, something from chemistry class. So in this particular thing with the sound, moving parts of my neck, the sound waves come out. It is picked up by the microphone that I am wearing right here. That's why you guys can hear me hopefully clearly. The microphone works much the same as my ear, in that it has a series of devices that can pick up those pressure waves, and rather than turn it into words that it understands, the microphone is not that smart. Instead, what it does is it turns it into an electrical signal. It's the same basic idea as a wave through the air, except now that it's working in electricity. That electrical signal, because this is a Bluetooth headset, gets turned into a radio frequency, which is still more energy, because it involves the movement of light. That's what radio is. It's light. I know we're going way off tangent here. Well, that light is beamed over to my computer through Bluetooth. The computer then picks up the signal, which is going up and down, and it then records it and turns it into sound. A speaker then does the opposite by taking the signal and turning it into pressure. If you actually take apart a speaker or a pair of headphones, what you'll find is that it's actually just like a disc attached to an electric motor. And all that happens is the electric motor gives it a signal, gives it an impulse, a series of for lack of a better term, hits. And then the dish just moves back and forth. And as it moves really fast, it basically mimics what my throat was doing when I was close to you. The power of modern technology allowing you to hear the organized motion of my throat muscles all the way far away. Crazy, right? So all of this is very cool and all, but honestly, it's very complicated. I mean, let's think about this. I've been talking about light. I've been talking about waves. I've been talking about pressure. I've been talking about chemicals as well, right? I've been talking about chemical energy. I'm going through tons of different types of stored energy. I have some good news. We're not going to be doing all of that in grade 11 physics, okay? We're doing the basic stuff. So in grade 11 physics, because we've mostly been dealing with things like balls and cars and bricks and other boxes and things, we're going to break potential energy down into just two very simple things, okay? First one, our dear, dear old friend, gravity. And then the other type of potential energy that we're going to talk about is going to be called spring. Okay? So, gravitational potential energy, spring potential energy, they're just potential energy, which we remember is just energy that we have stored and that we can make use of at some point if we can just unlock it through the right methods. Gravitational potential energy is very easy, right? This, right now, has gravitational potential energy. Energy is stored in it. How do I know that? Because if I move it so it is no longer supported by the table, it's going to fall. That's it. Falling is motion. So up here, it had the ability to move. It It just couldn't access it. It was potential. It was stored. Once I move it over, now there's nothing stopping it from moving, so it moves. That's it. We're done. Okay, fine. You want an equation. The equation for potential energy due to gravity is super simple. The energy of gravity is equal to mgh. Mg is, of course, force of gravity. H. H is what? Let's think. H. Yeah, it's height. Wait a second. Height is just another thing for displacement. He says. There's the work equation. Well, isn't that shocking? If I do work, I give it energy. So, yeah. The energy due to gravity is just how high off the ground have I raised it. That's it. Now, springs are a little more complicated. Let's think of it this way. Okay, so gravity is us storing energy by lifting stuff off the ground, right? And then everything wants to fall to the center of the earth because that's how gravity works. So that's just us making use of a naturally occurring phenomenon. Well, a spring is very similar, right? A spring is what we've got right here. This is a spring. If I pull it, it stretches. If I let go, it compresses. It becomes slack. This is a spring. Oh. What can I say? I never had enough chance to practice, huh? So an elastic is a spring, and the way it works is that if I compress a spring or stretch a spring, it will require a force, and there will be a displacement. As I stretch the spring out, getting more and more displacement, what happens? I'm storing energy in it. Think of a spring, heck, both of them, gravity, spring, they're just a way to store energy for later use, much like how you store, the energy in the battery of your cell phone. That's electrical energy that you've stored in your phone for later use, and then when you turn on the screen, you're using that energy. That's why the batteries die. So, as long as I'm holding the elastic band taut, that energy is stored. It is there. It is waiting to be used. The moment I let go, it releases that energy and moves. This follows our entire understanding of energy. Energy is motion. So long as it moves, it has energy. Done. Now the equation for this one is a little bit weird. The energy of a spring is 1/2 kx squared. That's how it's usually written. Now, K is basically how strong the spring is. Like, this is pretty easy to pull. If I got, like, all of these and tried to pull them all at once, it gets a lot harder. That's how resistance training works, right? You just try to, I'm going to work out, right? A big, heavy elastic. So this is how strong the elastic is, how difficult it is to move it. And it's measured in newtons per meter. This is just basically displacement again. It's how far I've stretched the spring from its rest position. So in the case of the elastic band, there's the rest position. I have now stretched it a tiny distance. If I stretch it a bigger distance, then I have more motion overall. So that's it. This one here, X will be in meters. This one here will be in newtons per meter, and they'll usually tell it to you. And then, of course, 1/2, well, it's very similar to this one up here, isn't it? It's very convenient. And that's it. These things both store energy. It's just a question of how they do it. So, I want to summarize all of these points, okay? And you guys have a great summary that I did up on the 3rd page of the notes, but here to repeat it. Energy is motion. Kinetic energy is energy being used now. This is stuff we use to move something this moment. And it has the equation 1/2 mv squared. Energy due to gravity and energy due to springs are both about moving later. They both move energy. They are both energy that can be used to cause something to move, but later, not now, some other time in the future. In the case of gravity, letting things go. In the case of spring, letting the spring go. Oh, geez, there's some similarities there. In the case of chemical bonds, breaking the bonds, which means you're letting the bonds go, I guess. Some similarities. These two, of course, have their own equations. This one is 1/2 k x squared. And this one is mgh. That's for Eg and Es. Energy is motion. The other thing that we said was that work controls energy. That's the other key of this. And what we talked about is the fact that positive work will add energy. Energy will go up. Negative work, energy will go down. And we said that the equation for work is equal to F delta D. So if there's no motion, if there's no force, there's no work. If you don't do anything, nothing happens. If there's no force or no displacement, then you get no work. The other thing is that if the force and displacement are perpendicular to each other, right? Like if I push really hard into the board here and then the board suddenly shoots up into space, I didn't do any work, something else made it move. So work only matters if it's in the same direction. It's very simple like that. If there's no work, there's no change in energy. And if there's no change in energy, this is key. If there is no change in energy, so if no work, then there is no change in energy. That means the energy that I start with is equal to the energy that I end with. Remember when we were doing in just the other video about how I lifted the weight and it had 1960 joules of energy, and then I dropped the weight and it landed on my foot? How much energy did my foot get? 1960. Why? Because nothing did any work in that. The energy just got transferred from one thing to another. This is the same thing that happened when we were dealing with the Newton's cradle. The energy was transferred from one thing to another. As the energy was transferred, each one gets the energy until eventually it gets to the end, and then nothing stops it from moving. This is potential energy, gravitational. When I let go and it swings down, as it's swinging, it's kinetic. As it hits, it stores the energy potential, 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 potential. All of these are in many ways spring. Then it gets to the end, and it moves again, kinetic. And of course, potential when it's at the top, and then it comes right back down. There you go. Energy shifts and moves and bends and warps. It moves around, but there's nothing new going on. It's just changing where it is and how I'm storing it. It's in my wallet, it's out of my wallet. It goes into the bank. It's in the bank, I want to take it out, make use of it again. That's it. So, let's do an example and see what we can put together here, okay? Remember, energy is motion. That's the key. Now, there is a simulation, PhET simulation. Hopefully you guys did one in the dynamics unit. There's another one for energy, and it's very good. But the problem is that I'm not really sure how I can show it to you guys. Not with the setup that I have. I don't know. Maybe I'll see if I can come up with something. But in the meantime, we can take a look at some energy. Examples. Sorry. So let's see here. The example we've got in the notes says we're going to have a dart gun, and we're going to shoot it from the floor. It says it uses 24 newtons of force over 0.25 meters. Will let you load the gun. So we've got our gun down here, and you guys unfortunately didn't get a chance to do this particular particular exercise. So this particular, you guys didn't get to do this lab, which means this particular exercise does not immediately make you all feel dread and then relief once we get to the end and you realize how much easier this is going to be. So to load the gun, I have to move it 0.25 meters, and it takes me a force of 24 newtons. Okay? So first one, how much energy did I use to load the gun? That's super simple. Work is equal to energy. Work is how I loaded the gun. I applied a force over a displacement. So I'm going to do that, and I'm just going to get force times displacement equals work. Work equals 24 times 0.5. Work is going to equal, I think, about 6 joules. Now, is it positive work or negative work? Well, let's think about it, right? I had the gun, and then there's a plunger at the back that I pull back in order to load it. Well, I'm applying a force going backwards, and it's moving backwards. So it's positive work. There we go. That's simple. I have added energy to the system, energy that I had to eat at some point. Okay, next one. How strong is the spring to store that energy? Okay, that's a little trickier. So the spring is storing the energy, right? Because once we pull back the plunger, it doesn't just like sit there until I let go. That's kind of how a bow works, for example, a bow and arrow, right? You hold the bowstring, and until you let go, it doesn't shoot. So I'm holding it pulled back, and then it locks and it holds. Well, the spring inside must be holding it. So how much is the spring doing? Okay, well, let's see here. The spring is 1/2 kx squared. Okay, well, we know how much the spring moved because we know how much we moved it back, 0.25 squared. K, I don't know, that's what I'm looking for, 1/2. Well, do I have the energy? Well, of course I do. The energy that I put into the system is the energy the system has. So this must be 6 joules of energy. Oh, well, that's pretty straightforward. If I solve this for K, I'm going to get a nice 192 newtons per meter. So that means that it would take you 192 newtons to move that spring 1 meter. That's it. That's all it means. It just basically tells you how strong the spring is. Okay, C. How much energy will the dart have at launch? Okay, well, I pull the trigger, and the dart goes flying. How much energy does the dart have? Well, how much energy did I give it? 6. Okay, but how much energy does it have at the top of the arc, right? Like, sure, okay, here it's got 6 joules, but how much is it going to have here? Surely it must be different. It's higher in the air. Except, at any point, did I do any work? Did I ever take any energy away? Did I apply a force? I didn't. So the energy in the system must be the same. So up here, I'm going to have 6 joules of energy. Oh. Well, what about at the bottom? Well, it's again, no force. So still, down over here, it's going to be 6 joules of energy. What about, like, right here? How much is it going to have? Same amount, because nothing has changed. It's still 6 joules of energy. The amount of energy stays the same because nothing is doing any work to change or control how much energy the system has. Okay, what's the muzzle velocity if the dart has a mass of 0.1? Okay, so this dart right here has got a mass of 0.1 kilograms. So muzzle velocity is the name that we give to the speed of something as it leaves the end of the gun. Again, you guys would have done this a lot if we had managed to do those labs, but we didn't, so well. So muzzle velocity, okay, well, velocity. There's only one equation that has velocity in it, and that's going to be this equation. Okay, well, we know how much energy it has. It's got 6 joules. And we know 1/2, because that doesn't change. The mass we just said was 0.1, so what's the velocity? Oh, well, okay. That should be pretty easy. We just solve for it, and we're going to get that it's got an 11 meter per second velocity. Okay, pretty straightforward so far, right? It's just about knowing what things they're asking and how to set it up. So what's the velocity of the object at the top of the arc? Now, hopefully we remember this, right? For projectile motions, anything that you go put up in the air, when it gets to the top, it stops. So up here, the velocity is 0. So if the velocity is 0, does it have any kinetic energy? Well, if I make this 0, everything becomes 0. So it's got no kinetic energy. So where's the energy? Because we just said the energy doesn't go away, but the kinetic energy is 0. Gravity. right? It's not moving, at least not up and down anymore, but it is up in the air, right? The moment that if I were to let go, if I were to put an object there and then let go, it would fall. So this object at the top of the arc has no kinetic energy, but it has 6 joules of potential gravitational energy. And that's the big difference. Okay. Way down here at the floor, what's its potential energy there? Okay, well, it was loaded in the gun, it had a spring. The spring energy is potential. Okay, so we could say that. We could say that before I pulled the trigger, right, this thing had a spring energy of 6. Right after I pulled the trigger, kapoom, the dart flies out. Spring energy goes to 0. It has to, because the spring is no longer under tension. It's not up in the air yet, though, but it is moving. So it has kinetic energy of 6, but it has no potential energy of 6. So this would become 0, and the spring becomes 0 at the moment that it is flying out of the barrel. What about here? Let's say this is halfway to maximum height. There's 6 joules of energy in total, but I'm halfway up. Well, at the top, I have 6 joules of potential. And at the bottom, I have 6 joules of kinetic. Halfway up, I'm going to have half and a half. Halfway up, I'll have 3 joules of kinetic. And 3 joules of gravitational potential. Now, could we have spring potential? Yeah, we could, but we don't have a spring halfway through the air, so that doesn't come up. Okay, well, how high will the dart reach? We could do that with kinematics, but we can also do it with energy. We know that the dart is going to go, let's see here, height of the dart. Well, Eg equals mgh. We know that it's going to have 6 joules at the top. We know the dart weighs 0.1. We know 9.8. We can find h. And in this case, h will be about 6.12 meters. How fast is the dart halfway up? How fast is the dart right here? Well, here we know the velocity is 0. And here we know the velocity, because we calculated it, was 11. Well, what is it here? It's not going to be half. Or will it? How do we solve that problem? What do? Halfway up, we go E, F. Technically, my bad. Trying to at least vaguely line up the questions in the notes here. The height of the dart is g. H is how fast is it halfway up. Well, halfway up, we're looking at how fast. It's still energy kinetic, 1/2 mv squared. We don't have 6 joules of kinetic energy there, do we? No, we have 3 only. The mass is still the same. It's still 0.1 v squared. Solve for v. We plug all that together, and we're going to get 7.5. Because, of course, the key is half the energy, it's not gone, it's just in a different form. It's being stored for later use. That's all. So the next one I have is that what happens if the dart comes crashing down on a spring? Dart hits the spring, and we're going to say that this spring has got a compression value of 200 Newton per meter. So in that case, this is going to be I. How much is a spring compressed? So I'm looking for D, so this is going to be ES is going to be equal to 1/2 kx squared. The ES, well, what's the energy at the bottom? Oh, we said it's 6. And once it's 6, and all of that energy is going to get stored in a spring. Right? So the dart comes down, it hits the spring, and it just compresses the spring and stores all the energy. Okay, so this is going to be 6, and this is going to be 1/2, and then the k, it tells us, is 200, and then we're looking for x squared. All right, so we just solve for x, and what do we get? I don't have this one written down, unfortunately. Some of you who have looked through the notes will notice that some of these questions are just little sticky notes that I attached to my notes because I haven't really had a chance to expand on them yet. So we'll do this one together here. Let's see, 6 times 2 divided by 200, square root. It's going to compress it 0.25 about, we'll say, kind of cheating on the rounding there, but we're going to pretend. 0.25 meters, so not very far. That sounds familiar. Wait a second, what was the strength of our spring? 192. Oh, so it's going to be about the same, isn't it? Ooh, look at that. Everything's lining up. J, if the dart flies off the spring, how high will it go? Right, so I compress the spring down, and then what's going to happen is the dart, well, there's nothing holding the spring down, so the dart's going to be shot back up in the air. Well, how high does it go? Well, how much energy does the dart have? It's still 6, right? That's how much I loaded it with. Nothing has taken the energy away. There's been no work yet, so it's still 6. So once the spring has stored the energy, it then releases the energy, shooting it back up in the air with 6 joules of energy. Well, how high did it go in the air last time it had 6 joules of energy? 6 meters, give or take. Guess how high it'll go this time? 6 meters. That's it. So, the last piece of this whole thing. Who knows what letter I'm on now? One in here says H. That doesn't make sense. That should be K. So if I catch the dart over 0.1 meters, now the dart has gone up in the air and I grab it and I catch it over 0.1 meters. How much force do I need to use? Well, I need to stop it from moving. I need to do work. I need to take energy away. I'm looking for this, and this is going to be 6. So once again, I take my trusty calculator and I go 6 divided by 0.1. The force is going to be 60 newtons. If I want to stop that after its roller coaster of boing, catch, I have to use 60 newtons of force. Otherwise, it'll keep going until I stop it. It won't stop. But speaking of stopping, that's it. There you go. That is energy, and this is an example of an energy question. And what you'll see is the key thing is this diagram as we were sort of scribbling things in here. The energy stays the same, but what form the energy is changes. So at different times, the number was either 6 or 3, depending on what was going on. Of course, that also means that if I asked you for the total energy of the system, right? Like if I said, hey, what's the total energy? We know how to do the word total in math. That's just the sigma, sum. The total energy of this system. Well, here it's 6 because it's 6 plus 0 plus 0. Here it's 6 because it's 3 plus 3. Here it's 6 plus 0. Here it's 6. And on the spring, it was going to be 6 plus 0 again. So the total energy can always be written as a sum of all the pieces that we have been talking about. Now, do you need to do that every time? No, but you will see that this equation, this style of writing the energy, will come up in the practice problems because it can be useful at times. But at the end of the day, all we're talking about is how does all this stuff come together. Okay? Just remember, energy is motion, kinetic, potential energy. They're just different ways of storing that motion. Sometimes it's stored, sometimes it's being used. That's all. Nothing else. It's very straightforward. This unit is generally much easier than many of the others. If you're confused, of course, ask questions. I'll toss up some answers and such online. Enjoy some nice weather out there, guys. We've only got 2 weeks. Usually I'll take about 1 week to do energy, and I'll take 1 week to do momentum and impulse, and then we're done. So you guys are almost finished. Congratulations. Cheers.